Am I audible? Okay. So we'll wait for another minute. So this is the first question of the day. Okay, before that, let's go to the web page once. I will share the entire screen. So we have come to week 4 of this course. Since this is a 4-week course, therefore this is the last week in this course, and we have seen multiple lectures like BFS, DFS, Dijkstra, Bellman-Ford. So lecture 20 is Floyd Marshall. This is incorrect. The name of the algorithm is Floyd Warshall. So it should be W and not M. So I think this is a typo. So look at the questions that were offered last year. So if you have other questions, then you can ask me. But first, let us look at these questions which were offered last year. So if you're not able to see the screen, then please let me know. All right. So the first question is about Dijkstra's algorithm. So you have seen that Dijkstra's algorithm is the simplest algorithm for finding single source shortest path in a graph. And generally, we have seen the algorithm in the weighted setting where the edges have weights, and we have seen it in the context of directed graphs. So we have seen that for finding the shortest path from a given source to all other vertices, this algorithm uses a greedy strategy. And as part of this algorithm, there is a step where the minimum weight, or rather, I would say the minimum distance from a given set of distances have to be found. And that is done using a priority search tree. But if the weights are all same, then that requirement of finding the minimum will not arise. So unweighted means what? Let me write down. So unweighted. Okay. Okay. So unweighted means you can say that every edge has same weight, or let us say unit weight, one weight. Okay. Is the meaning of unweighted. So the graph is given to be unweighted in this question. Additionally, uh, we expect linear runtime. So linear runtime means what? Order v plus e. So what does v plus e mean? So v is the number of vertices equal to the number of vertices in the graph, and e is the number of edges in the graph. So you're expecting a runtime like this. So the main bottleneck, the reason the running time of Dijkstra is V plus C log E is because of this priority search tree. So what the priority search tree is the bottleneck for the running time. So what data structure will help us? Should replace this tree? There is a question. Oh, sorry. I mean, there's a priority queue. There's a priority queue which is used in general, right? Yeah. So instead of a priority queue, what data structure should be used so that the running time is order V plus C? So because the edges are unweighted, everything has equal weight. So therefore, it does not matter in which order, you process uh, the adjacent vertices to a vertex, because the order doesn't matter. So you can do it first come first serve. So because you can do it first come first serve, so what data structure supports first come first serve? Yeah. So Q supports first come first serve because the graph is unweighted. So you don't really bother about being greedy. So being greedy doesn't help. Although the algorithm itself is greedy, it tries to extract the minimum out of the priority queue, but finding the minimum is no more necessary. Therefore, a Q will work. So I will choose Q as an answer. So what is the mode of operation for stack? It's first come, last come, first serve. So stack is last in, first out. Since Q is FIFO, first in, first out. So therefore, I'm taking a Q. Okay. So let us see what is the answer. So A is the answer. We are right. So any doubts on this question? We will move to the next question. So which of the following is not a greedy algorithm? So you have seen Dijkstra, Bellman-Ford, Prim's, and Kruskal's. Prim's and Kruskal's algorithm are for finding the minimum cost spanning tree, and Dijkstra and Bellman-Ford are for finding the single source shortest paths. So one of the algorithms here is not greedy. Remaining things are greedy. So which one is not greedy? So I already said that Dijkstra is greedy. So since Dijkstra is greedy, it is ruled out. How about the others? So how does Kruskal work? So you're given a graph. In the graph, you want to find the minimum cost spanning tree. So minimum cost spanning tree is a tree of minimum sum of the weights of the edges, and also spans, means covers, all the vertices of the graph. Spanning tree of a graph G is a tree of minimum sum of the weights of the edges, and also spans all the vertices of the tree. So what does Kruskal do? It chooses the minimum weight edge first, and then it checks that whether the second uh, I mean, so there is a lowest cost edge that is taken, whether the second lowest cost edge can be taken or not, and so on. So as long as there is no cycle introduced, as long as it remains a tree or forest, it keeps adding edges, but it does so in the order of increasing order of weight. So it has to find the minimum. So whenever you are doing something minimum or maximum, you are being greedy. So therefore, Kruskal is also Kruskal is also greedy. So is D is also ruled out. Yeah. So how about Prims? So remember that Prim's algorithm, Prim's algorithm is essentially a modification of the Dijkstra's algorithm. So Prim's algorithm is for finding the minimum cost spanning tree. Dijkstra is for a different purpose. It is for finding the single source shortest path. But if you read carefully, you'll realize that Prim's algorithm is nothing but it's a modification of Dijkstra's algorithm. So therefore, this is also greedy. So therefore, C is also ruled out. So why is B not a greedy algorithm? Why is Bellman-Ford not a greedy algorithm? So the answer is C, but sorry, Bellman-Ford is B, right? What am I doing? Prim is at Prim's algorithm is what? C. I think some auto edit is happening. That's the problem. Oops. Okay, fine. So C is Prim's. Prim's is ruled out. Uh, we have ruled out D because Kruskal is greedy, and A is ruled out because Dijkstra. So okay, so why is Bellman Ford not a greedy algorithm? Anybody? So what kind of algorithm is Bellman-Ford? If not greedy? So it's a dynamic program. So an algorithm is a dynamic program algorithm. How do you identify that this algorithm is dynamic programming? So whenever you see that a table is maintained, table of values is maintained by an algorithm, you would guess that it's a DP. Okay, so you have seen that in the Bellman-Ford algorithm, a table is maintained, and the entries of the table are computed based on the entries of the already computed values. So you have the table, you're looking at the ijth entry. So this is computable by looking at the values of the already computed entries. Yeah. So therefore, it's a DP and it's not a greedy algorithm. So the answer is B. B is not a. What is the question? Which of the following is not a greedy algorithm? So Bellman-Ford is not a greedy algorithm. It's a dynamic program. All right. Any questions on this? Any doubts? I'll let you read the question for a minute. So you have been given a graph. So in this graph, there are how many vertices? 9, right? So any spanning tree of this graph will have how many edges? How many edges so that it remains a tree and doesn't have cycles? You have 9 vertices. So you can see that there are many cycles in this graph. This is cycles, another cycle. So we want to get rid of all the cycles. So how many edges we should have in a spanning tree? So if I tell you that a tree has n vertices, okay, it's an independent thing. So I tell you that a tree has n vertices. Then how many edges are there? So a tree T, capital T. Yes. Yeah, because if it is n, n vertices, n edges means it is definitely one cycle. But with n minus 1, uh, we can ensure that the tree is connected as well as there's no cycle. So I'm saying a tree, I'm not saying a forest. Oops. I'm saying a tree. I mean, a tree, when I say tree, it by default means connected. I'll still write connected. So when a tree has n vertices, then the number of edges is n minus 1. Because if you add one more edge, then a cycle will be formed. Okay, so you can prove this statement by induction. You start with induction on the number of vertices. You start with one vertex, so it doesn't have any edges, 0 edges, and by default it's a tree. There are no cycles. You start with two vertices. Two vertices, you add an edge between them, so there are no cycles. Two vertices, one edge. This is also a tree, and then you can extend it by an inductive argument. So now I know that this graph has n vertices, 9 vertices. So in this graph, I'm looking for a minimum spanning tree. So I want to connect all these vertices using the minimum number of edges so that there are no cycles and it's one connected component. So every vertex is reachable from every other vertex. I want to delete some of the edges so that it becomes a spanning tree. So in the spanning tree, how many edges will be there? So there are 9 vertices. So 9 minus 1, 8 edges will be there. Okay. So now you have to identify that what are the 8 edges you will take and what options do you have. So you have to count the number of distinct minimum spanning trees for this weighted graph. So I'll give you a minute to think about it. So try to remember the Kruskal's algorithm. What does the Kruskal's algorithm do? So it identifies the lowest cost edge and includes it in the minimum spanning tree. So what is the lowest cost edge in this graph? Yes. So this is the lowest cost edge. This is another lowest cost. So how many one weight edges are there? One, two, three, four, five. So you can pick any of them and declare that this edge is definitely part of the minimum spanning tree. This is as per the Kruskal's algorithm. And this is a common sense also, that you want to form a tree, then you are definitely going to take the lowest cost edge. Okay. So now let us say that I take this edge. Okay. So between this vertex and the central vertex, this edge I take as per the Kruskal's algorithm. Then out of the remaining edges, again find the lowest cost edge. So now you have already taken a one weight edge. So now you have option to take one of these four one weight edges. But you have to ensure that whenever you take an edge, it should not form a cycle with the existing edges. Because if it forms a cycle, it is no more a tree. A tree is a uh, connected acyclic graph. No cycles. Connected but acyclic. So you take this one guy, you take another one edge. So these two edges are not forming a cycle. Next, you take this one edge. Again, these three edges not forming a cycle. Then you take this edge, one edge. So this edge is disconnected from this part. So definitely not forming a cycle. Then you take this last one weight edge. So you have taken all the five one weight edges and you convince yourself that you have not formed a cycle. Now, five edges are taken, but you have to take three more edges because you know that the total number of edges in this minimum spanning tree is eight. So now you have choice. Now you have choice which three remaining edges you will choose. So you know that the remaining edges have weight 2. So now which edges you will take? So you have to ensure that you are forming a connected acyclic graph. So far you have taken the one edges. So consider this edge 1. This has no connection with this side, this one edge. These three one edges are there, this one edge is there. So, so you have to ensure that these two things are connected. So this edge, which is of weight 2, it must be taken, because if you do not take this edge, then connectivity cannot be ensured. Okay, so such an edge whose inclusion is necessary in the tree is called a cut edge. So this is a cut edge. So you know that this edge has to be taken. So now you have taken this edge as well as five one weight edges. Now you have to take two more edges. So specifically out of these two edges, here is a edge to weight, here is another edge to weight. So out of these two, you will take only one, because if you take both, then that will form a triangle, which is not allowed in a tree. So you have a choice between these two. Okay, two choices here. Either you take this or you take this. So you will take one of these. Okay. Similarly, to connect these three edges, which is forming a path, each having weight 1, with this one weight edge, you can either take this two weight edge or this two weight edge or this two weight edge. One of these three you can take. So again, you have three choices. So now, depending on what choices you make, you get a distinct minimum spanning tree. All right. So now you can tell me that how many distinct minimum spanning trees are possible after the analysis I gave you. If you understood the analysis, then you can answer the question and find the correct option. Yes. So there are three choices here. There are two choices here. So in total, there are three into two, six choices. So you understand, you have three shirts to pick from, and you have two pants to pick from. Then how many distinct pairs of shirts and pants are there? So you can choose one of the three shirts and one of the two pants. So 3 into 2, 6. So that is the fundamental theorem of multiplication. Okay. So I'll show you. Uh, yeah, so this is the instructor's solution. Okay, so you can look at it for some time. The same thing. Just a second. Yeah. So he's saying that either you take A or B. Here you take either C, D, or E. So two choices and three choices. You can read it. Yeah. I'll let you read it. I'll make it slightly smaller. There is a mistake here. In the left side, we could either pick C or D or E. That should be the sentence. So that's why there are three options for the other age. All right. Is this fine? All right. So we'll move to the next question. Okay. So this answer is 6. Okay. So when does a graph possess a negative weight cycle? So when do you say that a graph has a negative weight cycle? So I'll let you think about it. So the weights are on the edges, and the weight of an edge could be positive or negative or zero. So when does a graph contain a negative weight cycle? Which options can we rule out? What is a negative weight cycle? So a negative weight cycle is a cycle whose sum of the weights of the edges is negative. So suppose you have a triangle. Okay. So suppose how to show a triangle? Uh, uh, Suppose I'm just trying to show a triangle. Suppose, yeah, then let me use some board or something. So suppose this is a graph and the vertices are A, B, and C. And I give edges weights. For example, I give weight 4 here, weight -3 here, and weight -2 here. Then what is the sum of the weights on this cycle? Yeah, -1. Other guys are there. We don't worry about the other edges. Otherwise, the edges are also there. We don't care about the remaining graphs. I only care about the cycle, and I'm saying that look, this is a cycle, and the sum of the weights on this cycle is negative. That is why this is a negative weight cycle. Okay. Now we get back to our question. So when does the graph possess a negative weight cycle? So which options can we rule out? Which is definitely not the answer. Can we rule out B? First, can we rule out B? Yes, because having a cycle is no guarantee that it is a negative weight cycle. So we can rule out B. We can rule out B. Now, if the total weight of the graph is negative, for example, total weight of the graph is negative, it could happen that the graph is like this. There are two edges only in the graph. So there was it's a graph on three vertices, two edges only, and this is the total weight on the graph is -5, but it is no negative weight cycle. All right. So therefore, we look at this option C, that the total weight of the graph is negative. That is no guarantee that there is a negative weight cycle. So we can rule out C as well. So can we rule out D? The graph has one or more negative weight edges. I mean, who cares? If it has one or more negative weight edges, it is no guarantee that there is a negative weight cycle. So we can rule out all these things. But what about A? If the graph has only one negative weight edge, wait. If the graph has one or more negative weight edges, that is no guarantee that it poses a negative cycle. If the total weight of the graph is negative, that is also no guarantee that it has a negative weight cycle. If the graph has one negative weight edge, then it is, so yeah, we can rule out everything. So none of the answers is correct. So no answer is correct. So do you realize why no answer is correct? What is the question you're asking? How a cycle is formed? A cycle will be formed if you have a situation like this. So this is a negative weight cycle. 4 minus 3 minus 2 is minus 1. Yes, we need one cycle. So what is the, there is no option which is saying that there is a negative weight cycle, right? So are you convinced that none of the answers is correct? So this is the question, and they're choosing C. The total weight of the graph is negative. That is incorrect. So I have given you an example. So here is a graph, ABC. The total weight in the graph is minus 5, but there is no negative weight cycle. Okay. So saying that a graph possesses a negative weight cycle only when the total weight of the graph is negative, that is incorrect. So this is an incorrect option. Let us see what is the explanation. So here is the explanation. When the total weight of the graph sums up to a negative number, then the graph is said to have a negative weight cycle. That is incorrect, in my opinion. Okay. So Bellman-Ford algorithm provides no solution for such a graph. Yeah, if the graph has a negative weight cycle, then the Bellman-Ford cannot handle it. But Bellman-Ford can handle graphs with negative edges. Even if all the edges have negative weights, Bellman-Ford will still be able to handle it. Okay. So in my opinion, this is not the correct explanation. So this is Bellman-Ford. So it says that the Bellman-Ford algorithm is a way to find single shortest paths in a graph with negative edge weights. Negative edge weights can be handled. Even if all the edge weights are negative, it can be handled. But if there is a negative weight cycle, then that cycle can be taken many times. So to improve the shortest paths. That's why negative weights cycles cannot be handled by Bellman-Ford. Okay. So I do not agree with this answer. I don't think any of the answers are correct. All right. So you have anything to say on this question? Otherwise, we'll move to the next one. I have no clue about exams. You have to contact NPTEL. My responsibility is limited to uh, discussing questions and conducting problem solving sessions. You can leave your email ID. I will try to, you know, contact NPTEL in such matters. And if you have a question that you want to ask, I can try to contact NPTEL and ask them to contact you to resolve your doubts. Okay. So we'll move to the next one. So let G be a graph with n vertices and m edges. What is the tightest upper bound on the running time of DFS. We have seen DFS, depth first search of G. Assume that the graph is represented using adjacency. This is very important. So the graph is represented using adjacency matrix. This is very important. Now you can think about it. I'll give you 2-3 minutes. Option B, that's what Kahan is saying. Okay. So how does DFS work? So DFS is starting from a source vertex. Okay. For the DFS, the input is G and a source vertex where you start the DFS. Okay. So and then it has to look at, so first step is what? First step is find a neighbor of S. So you get to one neighbor and find a neighbor of that neighbor and so on, and you go and then you backtrack. Then you backtrack. So after you backtrack, you have certain back edges, you have certain tree edges. Okay. So now you know that the graph is represented as an adjacency matrix. So just to scan the adjacent vertices of a given vertex, you need order n time, because you remember how the adjacency matrix looks like. So the matrix is, so the adjacency matrix is n cross n. Okay, so there are n rows and n columns. So to scan that what are the neighbors of a given vertex, you need to go through one entire row. Okay. So we would have been able to do it in order m plus n time, in fact linear time, if we use adjacency list. So when what happens in adjacency list, you know that how many neighbors are there, and for a given vertex, the adjacency list has size equal to the number of neighbors. So basically, the size of the data structures is order m plus n, number of vertices plus number of edges. That is the total size of the adjacency list data structure. But for the adjacency matrix, the size of the data structure is n cross n, and you have to do a DFS. So that's why the running time is order n squared. My God. So you can read the explanation. So have you read the explanation? So at this point, we can take a break. I will show you the next question and we will take a break. When shall we come back? 7 8 minutes. Yeah, it's 6:56 now. So we can be back by 7:05. Can you hear me? Okay, so what do you think about this question? So you have this graph on n vertices. So you have done this DFS. So after DFS, you have got uh, uh, a DFS tree. Okay. So the thing is, this DFS tree need not be connected. There could be multiple components in the DFS tree. Okay. So if the DFS tree, so if the DFS tree had n minus 1 vertices, then it's a spanning tree. Okay. It spans all the vertices, covers all the vertices, as well as uh, it's one connected component. So in that case, see, the DFS tree had n minus, I mean, sorry, what I'm saying, edges. Sorry, the DFS tree definitely has n vertices, but if the DFS tree had n minus 1 edges also, then it's a spanning tree that we have seen a couple of questions ago. Okay. In that case, the graph has only one component, only one connected component. Okay. So what happens when you do DFS? Some of the edges are taken, some of the edges are become part of the DFS tree. So for example, if you look at this graph, for example, I start with this node and do a DFS from here. So what will happen? I'll go from here to here and maybe here to here, 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 and then I may go here and then go here, then go here. Then I come back and I realize that this is not taken. I take this. So some of the edges become part of the tree, DFS tree, and some of the edges are no more part of the tree. Part of the, I mean, they're not part of the tree at all. So how many? In this case, there is only one connected component in the graph, and because there are 9 vertices, you know that any spanning tree, including the DFS tree, will have 8 edges. So if the number of edges is n minus 1, that is strictly one less than the number of vertices, then there is only one connected component. So if the graph has n vertices and you realize that the DFS tree had n minus 1 edges. If the DFS tree had n minus 1 edges, that n minus 1 3 edges. Edges means 3 edges, nothing but 3 edges. Whatever are in the DFS tree are 3 edges. Whatever is not there, those are back edges. Okay. Then there is only one connected component. Now what you have been told is that in the DFS tree, there are k edges. Okay. Then how many connected components are there in G? Now you can try to think in few minutes. You can try to think. So you know that if k was equal to specifically, so you know that if k is equal to n minus 1, then there is one connected component. Now you can try to think. Yes. Yes. So I mean, it's very simple. So you can just do it blindly also. You know that if k is equal to n minus 1, then the answer is 1. Okay. So here, instead of k, you put n minus 1. So n minus 1 is so the first option is ruled out because you know the answer has to be 1. Second option is also ruled out. Third option, if you put k is equal to n minus 1, then you get 0. That doesn't make sense. Third option, you put k is equal to n minus 1, you get n into n minus 1 is 1. So the answer is D. This is clear. But let us understand this intuitively. So you realize that there are k edges in the DFS traversal. K edges are marked as 3 edges. So suppose that there are C connected components in G. Let me make C capital so that it's easy to recognize. Suppose that there are C connected components in G. So in each of these connected components, the number of vertices is one more than the number of edges. Okay. So in each of these connected components, you lose one edge. Okay. So that means you have total number of edges that you have is n minus C. But you have been told that the total number of edges in the DFS tree is k. So therefore n minus C is equal to k. In each connected component, you have lost one edge. So in C connected components, you have lost C edges. Therefore, total number of edges is n minus C, which is given to be k. So this implies that C is equal to n minus k. That the number of connected components is n minus k. Because you have to lose n minus k edges out of n so that you are left with k edges in the tree. Is that all right? Okay. So what is a simple graph? A simple graph is a graph that has no self loops. So what is a self loop? That a vertex is connected to itself by an edge. That is a self loop. So in a simple graph, such a thing cannot happen, and no parallel edges. So what is a parallel edge? Anybody, what is a parallel edge? So there are multiple edges between the same pair of vertices. Yes. Yeah, no, no. So suppose there is a vertex, if two vertices U and V are connected via multiple edges, let us say E1 and E2, then the edges are parallel. So now in a simple graph, the number of edges is equal to twice the sum of the degrees of the vertices. Is that true or false? Why is it false? Two times sum of degrees. Okay. Consider a graph. Here is a graph. So consider any edge. For example, this edge. Okay. So this edge is between this vertex and this vertex. So whenever we count this edge, the sum of, or rather, the degree of this vertex is how much? 1, 2, 3. So the one of the degrees of this vertex is corresponding to this edge. Similarly, this vertex has degree 2. One of the degrees of this vertex is corresponding to this edge. So whenever you counted an edge, there is a contribution of 1 plus 1, 2 degree in the total sum of the degrees. So what is the sum of degrees? So you take the degree of every vertex. For example, this vertex has degree 3, this vertex has degree 2. You take sum of all these degrees, add all these degrees. That is the sum of the degrees. So whenever there is an edge, you get 2 times 2 contribution in the sum of the degrees. So sum of the degrees is strictly 2 times than the number of edges. So the number of edges cannot be 2 times. So the number of edges is only half. So the number of edges is only half times the sum of the degrees, isn't it? So therefore, this cannot be true. All right. Yeah. So we have the next question. For a given graph G, this graph, which of the following statements is true? Is this a complete graph? Is this a complete graph? So what is a complete graph? So a complete graph is what? A complete graph is a graph where there is an edge from every vertex to every other vertex. A complete graph is a graph where there is an edge from every vertex to every other vertex. Now, is this a complete graph? Yes. Why is this not a complete graph? Identify two vertices having no edge between them. A and D, no edge. B and C, no edge. D and E, no edge. So it's not a complete graph. So A is ruled out. G is not a connected graph. What is a connected graph? A connected graph means graph. A connected graph is a graph where every vertex is reachable from every other vertex. There is a path from every vertex to every other vertex. So then we call it a connected graph. So is this a connected graph? It is a connected graph. So B is ruled out. The vertex connectivity of the graph is 2. What is the vertex connectivity? So vertex connectivity is, so let me put it this way. If k vertices can be deleted to disconnect the graph, then the graph is k connected, or rather k vertex connected. Similarly, if k edges can be deleted to disconnect the graph, then the graph is k edge connected. So the vertex connectivity of the graph is 2, means 2 vertices can be removed, and when you remove a vertex, you also remove the edges incident to that vertex. So 2 vertices and the incident edges can be removed to ensure that the graph becomes disconnected. That means there are multiple connected components in the graph. The graph is no more connected. So then we say that the graph is 2 vertex connected. Similarly, if there is an edge which I can remove to ensure that the graph is no more connected, then that's a 1 edge connected graph. So the edge connectivity will be 1. Okay, why is option C correct? So which 2 vertices? So he's saying that, Ghani is saying that option C is correct. Then we have to ask that which 2 vertices can be removed to disconnect the graph. Yeah. So if you remove B and C, you observe that E is connected to the rest of the graph via these 2 edges only. So E has only 2 neighbors, this guy and this guy, B and C. So if you remove both the neighbors of E, that is B and C, if you remove B and C, then what will happen? You will remove all these edges also. So these 2 edges will get killed. Sorry, you have removed B and C. So this edge, this edge, this edge, all this, and these 2 edges. Oh, all the, yeah. So all the edges are either connected to B or C. So the graph becomes completely disconnected. Right. On the other hand, if you remove, yeah, so these neighbors are also B and C. So if you remove B and C, see, these 3 edges are incident to B, and the remaining 3 edges are incident to C. So all the edges got killed. So there is no way for you to reach E from A or reach A from B. So therefore, B and C can be removed to make the graph disconnected. So therefore, C is correct. Okay. All right. So we'll move to the next question. So what is the maximum possible number of edges in a directed graph with no self loops having 8 vertices? So 8 vertices, 8 vertices in the directed graph. You want to ensure that what is the maximum number of edges in this graph is what? So before that, this option D is incorrect because there is no edge that can be removed to make the graph disconnected. So whatever edge you see, there is a cycle here. You cannot remove one edge and make it disconnected because there are cycles in this graph. It's not a tree. In a tree, you can remove one edge and make it disconnected. So why is it 56 or 56? Why is the maximum number of edges 56? Yeah, so from every vertex, you draw a directed edge to every other vertex. So there are 8 vertices. So from every vertex, you can generate 7 edges. So the total number of edges is 56. So see, if it is a undirected graph, then the answer will be 28, right? Because in the undirected graph, if you make a complete graph, then every vertex has degree 7. So the sum of the degrees is 7 into 8, 56. But an edge from A to B and an edge from B to A will be considered same because the graph is undirected. In that case, the total number of edges will become 56 by 2, that is 28. But in this case, because it's a directed graph, the answer is 56. All right. This is the last question of the day. So you have seen the Bellman-Ford algorithm. In the Bellman-Ford algorithm, the for loop, the main for loop executes how many times? Is it the number of edges times or the number of vertices times or one less? So remember the Bellman-Ford algorithm. This is the single source shortest path algorithm. And remember what has really happened, how you have formed the table. So here is the Bellman-Ford algorithm pseudocode. So this is the for loop. It runs from 1 to n minus 1, where n is the number of vertices. And then for every edge, it has another nested loop. There is an inner loop that runs for every edge, but the main loop that runs from 1 to n minus 1, where n is the number of vertices. There is another loop which is for detecting negative cycle, which is secondary loop. We don't worry about it. So if we assume that there are no negative cycles, then we don't need this part of the code. So I'll let you appreciate it. Then we can answer the question. So in a graph, when you are finding a shortest path and you know that there are n vertices, then the path length is at most n minus 1. So hoping that there is no negative cycle. If there is a negative weight cycle, then you can keep taking that negative weight cycle many times in the path and you will always get a better solution. But if there are no negative weight cycles, you will get a path, shortest path you will get. And you know that there are n edges, n vertices. So the path length would be at most n minus 1. So therefore, you have to relax. This is a relaxation step as per the terminology in Bellman-Ford. So at most n minus times you have to relax. So after running the loop n minus 1 times, you know that you have covered all paths of length at most n minus 1. So you get an update for each of the distances. So therefore, the answer is b minus 1. So we have come to the end of this assignment 4. So after that, the course has officially ended. If you're interested, then we can do one more extra session. In the extra session, we will discuss about something interesting. So whether the extra session will happen or not, I will let you know. Uh, all right. So this is officially the end of this problem of solving assignment sessions. Whether there will be an extra session or not, we will let you know. So if you have any questions, I'm here a couple of minutes. Otherwise, we'll close this session. Thank you. Thank you for attending. Thank you, Kavya. Thank you, Narasimhan.